The external gear pump is a rotary positive displacement hydraulic machine. It is widely used in industrial and mobile hydraulic circuits due to its advantages: compactness, simplicity, low cost, and high robustness. We'll calculate in application its performances. Here we show you the general shape of the pump from the outside, and then we also show you a disassembly demonstration to see how the components of this mechanism are assembled. Housing or casing. It contains the gears and precisely machined. Driven gear, spin freely. Drive gear, mounted on the input shaft. Shaft's input and output. Guided by plain bearings or rolling element bearings. Bearing or bushing. To guide the rotation of the gears. Seals. To guarantee the pump's watertightness against leaks. Just before starting the application, we remind you of the operating principle of the external gear pump. Don't forget to subscribe to the channel if you're interested in this content. 2 external gears, one driving, one driven, rotate in opposite directions inside a sealed housing. On the suction side, as the teeth disengage, the available volume increases, creating a partial vacuum that draws fluid in. The fluid is trapped in the spaces between the teeth and carried to the discharge side. On the discharge side, the meshing of the teeth reduces the volume, forcing the fluid out under pressure. Let's begin our application. Problem statement. An external gear pump has the following characteristics. Module, M equals 4 mm. Number of teeth per gear, Z equals 12. Face width, B equals 25 mm. Rotational speed, N equals 1450 revolutions per minute. Discharge pressure equals 100 bar. Suction pressure equals 0 bar, thus delta P equals 100 bar equals 10 megapascal. The measured actual flow rate is equals 0.65 liter per second. The measured actual torque on the shaft is, C actual equals 80 Newton meter. 1. The displacement volume and the theoretical flow rate. 2. The volumetric efficiency. 3. The hydraulic power. 4. The theoretical torque. 5. The mechanical power absorbed. 6. The mechanical efficiency. 7. The overall efficiency. Before moving on to the solutions, take notes. If you have any further questions to suggest afterwards, please leave them in the comments. To calculate the pump displacement and flow rate, the following formulas can be used, the first for volumetric flow rate and the second an approximate formula for the displacement. As you can see, the two characteristics to be determined depend on the module, the number of teeth, the width, and the rotational speed. Well, now we must convert units of module and width to meter. Then we use the formula of displacement, and as you notice after calculation, we find almost 3 by 10 power minus 5 cubic meter per revolution. Let's move on to calculating the theoretical flow rate. We apply its specific formula, of course, and we simply find approximately 0.73 liters per second. Internal leakage, clearances between teeth, between gears and housing, reduces the actual flow rate. The volumetric efficiency is defined as the quotient between actual flow and theoretical flow. Well, numerical application gives 0.892 or 89.2%. Hydraulic power is an important characteristic of the pump because it is determined by the product of the flow rate and the pressure difference. Therefore, after calculation using SI units, the hydraulic power is 6,500 W, or 6.5 kilowatts. Torque is a mechanical parameter used to select the drive motor. Its value is related to the pump's displacement, the pressure difference, and, to be more precise, the mechanical efficiency, which is the ratio between the theoretical and actual torque. In our case, the torque is 48 Newton meters. We now use the well-known formula in mechanics to determine power, which is torque multiplied by angular velocity. All calculations completed, we obtain 12.15 kilowatts. Let's return to the formula for mechanical efficiency, which is the quotient of the two torques, yielding 60%. And the overall efficiency can perhaps be calculated in two ways, as you can see, either by the ratio of the powers or by the product of the two previous efficiencies, volumetric and mechanical. In any case, our efficiency is 53.5%. The pump studied has a theoretical flow rate of 0.73 liters per second but delivers an actual flow rate of only 0.65 liters per second due to internal leakage. Volumetric efficiency equals 89.2%. The mechanical efficiency is low, 60%, due to significant friction losses, bearings, fluid viscosity. The overall efficiency of 53.5% means that more than 45% of the absorbed mechanical power is dissipated as losses. To improve these performances, one could increase the rotational speed, reduce internal